Hello everyone, I am Mirza Asif and I'm going to talk to you about effectively using 3D RAM. I will be starting off with explaining how 3D RAM is built and then explain advantages of 3D RAM, followed by various optimization techniques used in today's 3D RAM technology. Why did we even come up with using 3D integrated circuits at all in the very first place? The answer goes down to a very basic problem about technology scaling. In 1965, Moore predicted that the number of transistors in a chip would double every 18 months. The statement was quite true until the recent times. In the recent dates, the rate at which transistors doubling has changed from 18 months to a little bit over 2 years. However, with the increasing in the number of transistors on the chip, we have new problems named as dark silicon, when we cannot use all the transistors on the chip effectively. This has brought in a new possibility to explore the same amount of transistors in the z direction, or introducing the third dimension possibilities of exploration. How exactly are these 3D ICs built? There are two main ways to stack up the 3D ICs. The first method is face-to-face bonding, where both the metal layers of the ICs are connected together by a copper stub to form a 3D IC, and once the connection is made, the bulk silicon layer is chopped off so that the connections to the overall IC could be made, hence forming a three-dimensional integrated circuit. The second method is face-to-back bonding, where one of the two ICs is chopped off so that the silicon layer can be attached to the metal layer on the back of the other IC. In order to do this, a handle wafer is attached to the thinned IC, and once the connection via copper stub is made, both the ICs are joined together and the handle wafer is removed, hence forming a three-dimensional integrated circuit. The main advantages of using 3D integrated circuits is that it gives an extension to the present Moore's law. That is, being able to stack more number of transistors on the same chip. However, this time it's vertical and not horizontal. Now, with the introduction of three-dimensional integrated circuits, each layer can be built according to the process and not just one type of technology. As shown in the figure, a 3D IC can be stacked differently with different technologies being able to handle different processes, hence making it much more efficient. This also introduces a possibility of using shorter interconnections to reach a particular destination on the chip. With 3D integrated circuits, we can now search for data vertically instead of searching for it on the other corner of the chip. With effectively being able to search handle data now, we can limit the total power dissipated and maintain the same area across the chip with much higher efficiency. In the first optimization technique, we tested 3D DRAM across various processes, and three cases were considered to check the efficiency of 3D DRAM. The first one where a 3D DRAM was used like a cache-like memory, and PCM was used as a secondary storage. You can see the results from the above graphs represented. An average of 18% better performance was displayed by a 3D DRAM. However, the power consumption was higher than expected baseline configuration. In the second case, there was where 3D DRAM was used as a last level cache in the same system, and the performance measurements were taken. There is a similar pattern shown as the first case, where the 3D DRAM gives an average better performance of 27.3, and this helps. This data is clear because of the above mentioned advantages. However, is still increasing in energy consumption of 3D DRAM. Since this module, the last level cache is bigger than the normal cache, there is an increase in energy consumption. The last memory optimization, where an average performance gain of 49% was observed when 3D DRAM was used as a part of main memory. In these three experiments, the distance from the processor to the 3D RAM was changed and observed. Since now 3D DRAM is the farthest from the processor, it consumes a lot more power to perform the same instructions, hence increase in power. The other method of optimization used was the reorganization of 3D DRAM. In order to perform tests on a new system, on the system of a new 3D DRAM was developed from scratch, and the following inputs were given to the 3D DRAM generator. And the outputs were calculated, and these outputs were fed into a System C simulator to measure the performance. A page a size of 1 kilobytes was measured and 64 input outputs per tile was taken. Changing this value of 64 input output tiles to a 128 did not give much higher results. Hence, the author has decided to use a 64 input outputs for the same experiment. In order to measure the efficiency of the generated 3D RAM, three different traffics were used to generate high speed, medium speed, and low speed data. And this data was compared to a LPDDR. And the results are as follows. In terms of power consumption and workload distribution, we see a reduction in the amount of power consumed, not only in the ideal workload basis, but also there is a significant reduction in energy consumed for the 0.5 gigabits per second. And in the last case for 1 gigabits per second bandwidth, since the LPDDR doesn't support such high speeds, we could measure only the 3D DDR, and we see a reduction in the energy consumed. Another interesting method of improving the efficiency is by removing the bump used in the conventional 3D integrated circuits. Since the bump is the major cause of heat dissipation, using a bumpless type should help reduce the total heat generated in the IC and hence increasing the overall efficiency of the integrated circuit. The last method of optimization that I have discussed over here is by using 3D WIS technology, where an optically interface is used for communication and not the conventional one. This increases the speed of operation as well as increases the overall channels present for communication. The architecture is as follows. In a 3D WIS module, a 3D WIS module is divided into 4 ranks, and each rank has 8 banks. Each bank is divided again into 128 sub-banks able to handle one cache line at a time. Now, with optical interface, we are able to manage up to 64 channels. However, we use only 40 wavelengths or channels, out of which 8 are used for control signaling. The results of 3D WIS technology are as follows. We get highly optimized results for the case of timing parameters, energy values, and area efficiency. The access latency is just about 19.5 nanoseconds from a whopping 36 nanoseconds. That is almost 45% reduction in the access time. And the energy consumption values goes down to 0.78 nanojoules from 7.45 nanojoules. That's almost 10-fold difference, and this is decrease, and there is a significant decrease in area occupied by the chip too. In conclusion, I would like to state that 3D ICs and 3D random access memories are going to be the future technology. As discussed above, while fabricating 3D IC, if we use a bumpless 3D IC to build our DRAM, it would be helpful. Techniques like reorganization of the memory and effectively using the memory organization along with using the new 3D WIS technology should help us move towards better, reliable, and efficient 3D integrated circuits. If not today, the future technology is definitely going to adapt the 3D IC in every product. Thank you.